We want to begin our next discussion getting back to something you've talked about in other courses, but from a different perspective, the idea of selection rules in spectroscopy. For vibrational transitions, there's only a non-zero probability of the transition occurring if the transition dipole satisfies this relationship. Basically, the transition dipole, the dipole change caused by the vibration, has to be non-zero in order for us to be able to see the transition. Because the amplitude of vibration is a function of time, we can expand the dipole moment in a Taylor series about the equilibrium bond length in this way. So here's dipole moment as a function of time. Here is the dipole moment. Here is the change in dipole moment as x is changed as the molecule vibrates, as the amplitude of the molecule changes due to vibration. There are second derivative terms and so on that could be part of this Taylor series, but generally speaking they are much smaller than we can be concerned with, and so we'll only concern ourselves with those first two terms. Now, in an earlier lecture we used the Boltzmann distribution to show that for vibrational transitions, only transitions that go from n equals 0 to n are significant, because most at room temperature the molecules will be in the n equals 0 energy level. So we substitute the spherical harmonics from chapter 7 and the expanded dipole moment in for the transition dipole. And look what we have here. These are the normalization constants for the spherical harmonics. The permanent dipole is a constant, so that can be pulled out in front. And then so we have the spherical harmonic for a particular energy level, the spherical harmonic for the 0 energy level, the rest of the wave function. And then here we have the transition dipole, also a constant, pulled out in front, and then the spherical harmonics. Now, the transition dipole in our previous equation was multiplied by x, so we have x here, and then the rest of the function. Now I want to bring that equation over to the next slide so that we can talk about it a little bit. This first integral is going to be 0 because these spherical harmonics are different orthogonal wave functions. So in order to when we multiply them by one another and take the integral, then we will see 0 here. Now the second term will be will be 0 if the entire integrand is an odd function. Think about it. The area under the curve, if we're working from here to here, is going to be on this side the negative of this side. It will add up to 0. So let's think about what that means. Since the 0 energy level harmonic is an even function, x times that will be an odd function, because an even function times an odd function is odd. So the integrand will be odd if the transition level that we're going to is even. Therefore, this function, the transition dipole, will be 0 if m is an even function, and so transitions are only allowed to energy levels where m is odd, so that we get a non-zero sum under the curve, a non-zero integral. So our most common and most visible transitions are going to be those that are from n equals 0 to n equals 1. Let's think about this in terms of infrared spectroscopy. The Beers-Lambert law relates the change in intensity of a particular wavelength of light as it passes through a sample to the concentration of that sample. So here in this equation I've listed here, dl is the width of the sample cell. We usually like to set that to be 1 centimeter. Intensity is the intensity of the light that we're passing through, the electromagnetic radiation. Epsilon at a particular wavelength is the molar absorption coefficient, how much light that molecule absorbs per mole. And so this is the change in intensity, the difference in intensity that we find on the other side of the cell at our detector. If we integrate that equation, we get that the fraction of the intensity that makes it through to the detector compared to the original intensity is e to the negative molar absorptivity coefficient times concentration times cell length, and remembering that molar absorptivity coefficient depends on the wavelength. Alright, so take a moment to pause the video and write this problem down. This is one that we'll work together next time in class. I'd like you guys to give it a shot based on the Beers-Lambert's law. The molar absorption coefficient for ethane is 40 reciprocal centimeter bars at a wavelength of 12 micrometers. Calculate that fraction in a 1 centimeter absorption cell if ethane is present at the normal contamination level of 2 parts per million, and then talk to us about whether it would be practical to try to detect ethane in a cell that size at that concentration. Then calculate how big a cell would be required at 2 parts per million to get a 90% absorption, a 0.9 I'm sorry, a 90% transmission, 0.9 transmission fraction. And then think about it. That's going to be a fairly long cell length. I'll let you calculate it on your own. We won't have any cuvettes that big. So the question is, how can we detect ethane at the parts per million level if we want to use 1 centimeter cells? And I'll give you a hint, it can be done, but we'll work that all out in class. Try it on your own, please, sometime in the next day or two. Now, as I mentioned earlier, the molar absorptivity coefficient does depend on frequency, and certain molecules will have wavelengths or frequencies that have a very high molar absorptivity constant, and we can calculate what those frequencies will be based on our quantum mechanics results from the previous chapter. Each atom of a molecule can be moving in any of 3 dimensions at any given time. That gives that molecule 3n degrees of freedom. If they move together in a way that maintains the shape of the molecule and moves the center of mass, we call that translational motion. So that uses up 3 of the 3n degrees of freedom, where 3n is 3 times the number of atoms on the molecule. If they move together in a way that maintains the shape but keeps the center of mass the same, in the same position, that's called rotational motion. And for linear molecules, there are 2 degrees of freedom used up that way. There are 2 ways linear molecules can rotate. And nonlinear molecules could rotate in 3 different dimensions. So the number of vibrational modes we expect to find is 3n minus 5 for linear molecules and 3n minus 6 for non-linear molecules. Now let's talk about that in a fairly small molecule case. We'll talk about a phenomenon we call coupling. CO2 is a linear molecule with 3 atoms, so 3n would be 9. Since it's linear, we'll look at 3n minus 5. That gives us 4 vibrational modes. And I want to talk about a couple of those vibrational modes because we see CO2 as having 2 equivalent CO bonds. But there are two stretching peaks associated with those CO bonds. One of them can be seen in the infrared, and the other can only be seen in the Raman. It does not meet the infrared selection rules. And let's talk about then the way that we think of CO2. When one C double bond O vibrates, the atomic positions and electron distribution throughout the molecule are changed. That would influence the other CO bond. So they don't vibrate independently, since they are the same bond strength and one is influencing the other one. They're going to vibrate in conjunction with one another. They are coupled harmonic oscillators, and we can see what we mean here in this diagram. So what we'll do is think of each of the two CO groups as a mass coupled to a wall by a spring with force constant K1. So this is representing a CO bond, this is representing a CO bond. And we model the couple as the couple of them, as a second spring with force constant K2 that connects the two oscillators. If we assume that for the symmetric case, carbon does not move and K2 never changes length, only K1 is factored in the vibration. And we would calculate that frequency here. The asymmetric, or really anti-symmetric stretch, carbon is moving in between the oxygens, and we would model that this way, where as K2 stretches, K1 is being compressed, and as K1 stretches, K2 is being compressed, and so both of those spring constants would be factors in the overall spring constant of that vibration, and we would calculate a different frequency using the same type of equation that we used previously, and we get this equation for handling this type of vibrational mode from physics. You probably derived that in physics 111 or 221. So we won't bore you with that derivation, but you can check your physics text if you are interested. Now, selection rules in rotational spectroscopy are going to be derived similarly to the way they were in vibrational spectroscopy, and what we'll notice is that we're only going to see rotational modes in our spectroscopy where the change in J, the change in level, is plus or minus 1. The derivation is a little bit long. We're going to skip over that in this case, but what we will do is show that it does hold for a specific case, and that's actually going to be our fifth example problem that we'll work together in class from this chapter. So we're going to use the eigenfunctions, total energy eigenfunctions, for the three-dimensional rigid rotor to show that the J0 to J1 transition is allowed, but the J0 to J2 transition is allowed. I'd like for you, again, to try this out on your own before we get to it in class, which will probably either be next time or the time after. As a hint, I'll tell you to focus on transition dipole arguments, and like I said, we'll work that out together later on.